Hi everyone, I'm Ahmet Enes from Bilkent Physics Department. Today I'm going to present a paper for BU Spin Journal Club. The name of the paper is Magnetic Damping Modulation in Iridium Manganese 3 Nickel Iron via Magnetic Spin Hall Effect. The paper published in 2020. These are the authors of the paper, as you can see here. Before diving into the paper, let me briefly talk about the outline of my presentation. I will first talk about the concepts and theory of the paper, and then move on to experimental setup and procedure. Along the way, I will give the results and comment about it. And in the end, I will finish with conclusion. First, let me first talk about chirality, since it plays a major role in the paper. Objects are said to be chiral if their mirror image can be superimposed with each other, like cannot be superimposed with each other, like your hands. And chiral objects can be superimposed and are not distinguishable from their mirror image. And chirality is a geometric property, as you can understand. And there is also another geometric property that plays an important role in our paper, in the paper. It is non-collinearity or collinearity of spin configurations. Although the anomalous spin Hall effect is known to be existing in ferromagnetic materials, due to the non-collinearity in antiferromagnets, we can observe anomalous spin Hall effect in the antiferromagnets due to their non-collinearity. And non-collinearity means that the orientation of spins, there is an angle and angular dependence between the orientation of the spins. They are not in the same direction or opposite directions, but there's a angular let's say difference between spin configurations. These two geometric properties are important in the paper, non-collinearity and chirality. And the mechanism in the iridium manganese 3 is as follows. Non-collinearity and chirality causes non-vanishing Berry curvatures and ferromagnetic-like behaviors in the antiferromagnets. In this case, it is iridium manganese 3. And these ferromagnetic-like behaviors can be said to can be like large anomalous Hall effect or Nernst effect or magneto-optical curve effects. And as well as these effects, there are other effects that we observe, like spin Hall effect is observed within magnetic spin Hall effect is observed within the iridium manganese 3, and magnetic spin Hall effect is the important concept in the paper. Like another important point in the paper is that why do we use antiferromagnets? Why are they preferable over ferromagnets? First, they are fast. They are displaying fast and ultra-fast dynamics. They are insensitive to magnetic fields and they exhibit no stray fields. Also, they display large magnetotransport effects, and they are also efficient source of spin currents. One question about the magnetic spin Hall effect is how and why exploring the magnetic spin Hall effect. Magnetic spin Hall effect can be examined under the condition of ferromagnetic resonance, and it is novel and new in the sense that it offers new ways for analyzing the magnetization dynamics in the magnetic materials. In the paper, the antiferromagnet that was chosen is iridium manganese 3. So we better talk about it more. So let me first begin with crystallographic structure of iridium manganese 3. It exhibits non-collinear geometry, as you can see here. There are two different colors, blue and pinkish thing, and orange, blue and orange. And in the blue one, the orientations are along the towards point the center, and the orange one points away from the center. So this causes a non-collinear geometry and chirality. And also manganese atoms form cogomalatis in 1-1-1 plane. And also another feature of iridium manganese 3 is that it exhibits giant magnetocrystalline anisotropy energy due to locally broken cubic symmetry of the manganese sublattices. Also, it provides a large variation of the anomalous Hall conductivities along different orientations, and the ratio of the anomalous Hall conductivities is 1/39. It is like almost 40 times higher than the other one. The 0-1-1 orientation is much higher in the sense that it offers a large anomalous Hall conductivity. And the magnetic properties of iridium manganese 3 is, as you can see here, it is as follows: around like 47 degrees. It makes a peak in the X-ray diffraction pattern. Also, in the figure C, you can see the hysteresis curves after field cooling in a magnetic field of 70 kilooerstat. There are two orientations for the magnetic field cooling: 001 and 010, and they are almost the same. This is the magnetic field, magnetic hysteresis curve after field cooling in the figure D, and it is at the temperature of 30 Kelvin. And figure E shows that shows the exchange bias. And one important point is that the iridium manganese 3 and permalloy bilayer is antiferromagnetically ordered at the room temperature, because the blocking temperature is around 380 Kelvin. So let me move on to the procedure and how the setup is made. The authors first produced a 20 nanometer thick epitaxial iridium manganese 3 films on MgO substrate, and it is orientated in 100 direction, and at the temperature of 570 Celsius degree, using a magnetron spattering technique. And also it is kept with titanium layer to protect the permalloy layer. After production, the
FMR measurements are made. This is the schematic for the FMR setup. The setup is made so that the chip is flipped, so that there is no shortcuts, and the current is along the titanium layer. Fmr results show that, especially B and E in this figure, that ferromagnetic resonance signals are around like 9 gigahertz, and the frequency is swept at a fixed, while a fixed magnetic field is maintained. More about FMR results. As you can see here, these are the results that were obtained. These are along different orientations, 001 and 011. As I said earlier, although damping for both crystallographic directions, 001 and 011, is practically the same, damping is increased significantly in comparison to a simple layer of permalloy. This shows that the interfacial coupling of the iridium manganese and permalloy modifies its dynamic properties. This means that although the damping for just simple permalloy layer is not changed, the overall damping is increased significantly. And by using FMR techniques, we measured the damping factor, and we can conclude that the damping factor can be attributed. There are 3 different contributions to damping factor. First mechanism is that damping factor is strongly phase dependent and is coming from the antiferromagnetic domains of the uncompensated spins. The second mechanism is that it's phase independent and arises from bulk spin orbit coupling within the iridium manganese 3 layer. And the last one is the magnetic spin Hall effect. And in this paper, of course, we want to explore the magnetic spin Hall effect especially. Another finding of iridium manganese 3 is that the DC modulation of the ferromagnetic resonance line width along 001. Basically, these figures shows that the line width variation as a function of the resonance frequency for the magnetic field applied along 001 and 011 crystallographic directions. And the result based on and the graphs are obtained by using LLGS equation. The line width function of the frequency can be written as you can see here at the end, and this factor is basically the magnetic spin Hall angle. And these graphs are basically saying that basically they say that we can observe that for the magnetic field applied along 001 direction, a change in the magnetic damping occurs depending on the direction, positive or negative. This doesn't occur when the magnetic field is applied along 011 direction, as you can see here. This indicates that a change of the current induced torques in permalloy as a function of the magnetic field due to the magnetic spin Hall effect of iridium manganese 3. Basically, this says that iridium manganese 3 layer allows for permalloy to exhibit different magnetization dynamics, and
magnetic spin Hall angle in this experiment was calculated to be around 0.33, which is consistent with the previous data and previous data that was obtained by other techniques. So this proves the compatibility and trustfulness of the technique that was used in the paper. And as I said earlier, the chirality is important for iridium manganese 3, since it basically transforms an anti-ferromagnetic material into a ferromagnetic-like material. So as you can see here, lattice 1 and lattice 2 are mirror image of each other. They are not mirror image exactly, but they can be switched between, meaning that lattice 1 and lattice 2, lattice 1 can be changed into lattice 2, and they are coexisting in the material. So how can we transform one into another? We can use either a mirror reflection or time reversal operation. Lattice 1 and lattice 2 by this way can be transformed into each other. And therefore, we can conclude with the help of time reversal that lattice 1 and lattice 2 will exhibit the same magnetic spin Hall angle. They are like shifted in space or time. So as for conclusion, we can say that bilayers of iridium manganese 3 and permalloy have strong modulation of electric current induced damping-like spin torques. Another feature of iridium manganese 3 permalloy bilayer is that the angular magnetic field dependence indicates that this damping-like torques originates from magnetic spin Hall effects in the iridium manganese 3. This is important in the sense that we can observe and differentiate magnetic spin Hall effect from other effects within the material. As I said earlier, there are 3 contributions to damping factor, and we need to differentiate the magnetic spin Hall effect from the rest of the effects. And chiral and another conclusion is that chiral antiferromagnet systems such as iridium manganese 3 can provide additional functionality for electric current control of magnetization dynamics with very different symmetries than what can be expected from conventional spin Hall effects. So by using geometry and non-collinearity and chirality of iridium manganese 3 or any other antiferromagnet, we can basically have more control on the magnetization dynamics of the material, and this may help us to explore different spin Hall effects. And another important point is that this is a novel approach in charge to spin current conversion, meaning that the charge to spin current is important and it determines the efficiency of the material. So by this way, we can maybe utilize different charge to spin current conversion. And that's it for me. Thank you for attention and listening.